Okay, so uh, next week is November already, and it's a short month, and we have a number of things I'd like to do. So first off, on Monday and Tuesday, we'll have Lab 3, and I'll go over that in a second. And then I'm also going to give you there's a kind of a journal paper project that I'll be assigning, and so I'll go over that. Both of these assignments are on the D2L website if you want to go there, and I'll go over them now. So one thing about the labs is that I guess the Tuesday afternoon, I think we had like 10 students, and then there was only like 2 students on Monday morning and Tuesday morning. So I'm sorry, this is yeah, the Monday PM, which was I think 2 o'clock, right? There's like 10 students. So Monday morning is at 10 o'clock, is that 9? Yeah, so need a couple of volunteers for the 9 a.m. and I guess, what is it, 10 on Tuesday? Or 11, 10 or 11, I don't know. Do you remember what it is? Is it 10? 10, yeah. And so if 2 students can go to the Monday 9 a.m. and 2 to the Tuesday at 10 a.m., that would make the labs a whole lot better, I think. So any volunteers for Monday morning? Additional volunteers? No. Who had been going Monday morning? 1, 2, 3. Okay. And he's been going too. So okay.
He was in the
last time he had to go to the Monday afternoon.
Yeah. Okay. And how about Tuesday morning? We have 1, 2. Yeah, we need a couple more. 3. 1 more. Oh. Come on, it's not that early. All right. Well, okay. So that maybe at least gets 2 out of the Monday PM class. All right. So Lab 3 is a reflection hologram lab, and so this lab will be kind of fun, I think. So basically, so this is a picture of what you'll be doing. So we're going to keep it really simple, and it works very well. So we'll just use basically 1 beam in the construction and in construction of the hologram, and so you'll expand the beam and not use a collimator. Just have the beam expanding, and we'll have this off at some distance away. That gives us kind of the more or less somewhere in the average to minimal range of exposure level or power level that we need at the sample, but we want to keep this distance, reasonable separation between the pinhole and the film. I'll mention that why we want that in a minute, and then just place the object right next to the hologram. Okay. And so what will happen is the light will come from the left here, my left, and then go onto the film, hit the object, and bounce back, giving you this counter-propagating beam. Yeah.
Are we using a second collimating lens, or are we assuming we're going to let it expand?
No, we just want like a point source. So we're going to have a point source out here coming in, illuminating the beam. So the reason why you'd like to do that is that when you reconstruct this, you may want to reconstruct it with like a flashlight or another point source that you hold maybe arm's length away from the hologram in order to view it. Okay, and you can also use the sun. Sun will work pretty well too. For that, you would want a collimated beam. But if you're not using the sun, inside, looking at it, in general, you'd like to have some point source that's some nice distance away for convenient reconstruction. So so this works pretty well. It's it's a fairly stable system, so it's a minimal number of parts basically, and but there's a couple issues with it. For one thing, there is some residual absorption in the film, and so the light that's illuminating the object is going to be somewhat attenuated by, well, it will be attenuated by that film in passing through it. So one thing for the choice of your objects, you'd like to have a fairly bright object. So if you have some object that you wanted to make a hologram of, feel free to bring it. But ideally, it should be something white or bright, not something that's dark or has shades of gray in it or something like that. It won't show up very well. But like traditionally chessmen or one of my students was getting engaged and she brought an engagement ring or something, made a hologram of her engagement ring, so things like rings and stuff like that. Coins work very well. I have a nice hologram of a collection of coins that I was given when I left IBM a long time ago. Anything that has reasonably good reflectivity will work pretty well, okay? Now, another little trick you could do that's good for making these reflection holograms is to kind of tilt this near the Brewster angle, okay? And so, again, the light's coming in, it's going to be polarized. Let's see. So we want it, say, polarized in this direction. Is that? Yeah, I guess you'd want it polarized in the plane. So we want to, so we actually do that. Rotate the laser in the mount, so now the polarization is in the plane of the table. Or we can use a retardation plate. We'll probably use that. So now you have the polarization coming in this way. And the reason you do that is we're not going to be able to use index matching like we had for the transmission holograms, right? Because that would block the object beam basically. And the reason we did that was in order to eliminate back reflections from the surfaces of the hologram. So in this case, the surface reflection that's the most problematic is going to be from this back surface that reflects off and then propagates forward, creating another hologram basically if you don't do something. So if you kind of tilt this plate at an angle which is equal to the Brewster angle, so this is, I guess, N2 over N1, where N2 is the index of the material, which is about 1.54, 1.55, something like that. What will happen is then that the reflected light, it's now in the direction of propagation, essentially, and you don't, yeah.
Are you doing the Brewster angle from the normal of the film or from?
Oh, I'm sorry, yeah. I thought something looked amiss there, yeah. So, okay, yeah, so, and this is a pretty large angle. It works, I think it's like 57 degrees or so. So it's a pretty big angle. But if you look at, the reflectivity of that polarization, it's going to kind of go almost, well, it will go to zero right at that Brewster angle because the field that's coming off is, so here's your field, oscillating field coming in, and then it reflects, and so now you have the light is trying to oscillate in the direction of propagation, and so if you think of this as a dipole, right? Dipole radiation, you don't get any field emission in the direction of the field, or of the oscillation, I should say. So you have, field components in this nice lobed pattern, but not in the direction of this is the direction of oscillation of the electrons there. So you can eliminate the surface reflection by using this Brewster angle technique to some degree. Okay, it's not going to be perfect, but it's better than not using anything. So that's a little thing you can do here to help improve the overall hologram. Okay, by again, so what you're doing is trying to eliminate that back reflection. Okay, so a couple things to do here is what you can do is take a small piece of film and measure the transmittance through that, and that'll give you an idea of what the object field is going to be, because that's going to attenuate it, and you'll get an idea of how low it is, and so you can get a beam ratio and an overall exposure power level for the hologram. And then for a reflection hologram, the exposure density is going to be greater than what you used for the transmission hologram. Okay, and we're actually going to deride this shortly, the next week or so. But for a reflection hologram, if we look at the efficiency versus delta n, all right, the efficiency is an asymptotic function. It's actually a hyperbolic tan function of an argument which has in it the delta n and product with the thickness. So this is like a grading strength parameter. We'll talk about that shortly. But the idea here, but the main point I'm trying to make here is that it's a function of this delta n, and it's just a kind of an asymptotically saturating function here, which reaches an efficiency of 1. So, and delta n is proportional to the exposure energy that you use for the hologram. So what you'd like to do is to expose this up to a level which makes sure it's in that saturation region, and it'll give you a better result for a reflection hologram. Okay. All right, and so then here on the questions, I have a couple of things for you here. Well, Brewster angle is pretty simple. Just use that formula. It's 57 degrees. But, I mean, you can calculate it and then see how close you can get to that angle for your hologram. Let's see. Then, okay, you can look at a couple of things here. You can see if, by rotating the film plane in the reconstruction, whether you get a higher efficiency or not. If you get a higher efficiency by rotating, that means that there was some change in the material, which is changing the Bragg condition for that grading. Okay, so that may not be much of a problem for the bare material, but it is a problem that you have to deal with a lot of other materials. Okay, so look for any changes. And another way you can determine that is to, if you look at this in a white light, look at what color the hologram is. Is it still in red? Is it orange? Is it yellow? If the wavelength starts to shift like that, that means that there was either some shrinkage or swelling, which is changing the fringe planes in that material, the fringe spacing in that material, the period. And so you're getting a different wavelength for doing the Bragg match. And also, remember when we had our, so here, for a reflection hologram, we're going to have a K vector that looks something like this, right? And then you have your two K1 and K2, your propagation vectors matching that. So if the K vector changes, then there's probably going to be a different if you're reconstructing it at the same angle or nearly the same, this is going to, this is going to change to some degree, and so you're going to get a different angle and possibly a different wavelength for that reconstruction, okay? So again, by looking at a color shift, you can start to see whether or not you'll have any change in that medium. It could be an index change as well as a shrinkage of the fringe planes, okay? And then I'd like you to calculate what the fringe spacing is. Again, since you have a tilted grating here, you're going to have to use the Snell's law of refraction going in to compute your fringe spacing. And then I'd like you to expand a little bit on that. And here I'm saying that let's use a collimated beam now instead of this expanding beam, just to make things a little bit simpler. And so we'll have a collimated beam that looks like that. Here's your hologram plane, your film plane, and then replace the object with just a mirror, which is perpendicular to your optical axis. So this light's going to come in and then bounce back like so. And so you're going to have fringe planes, I'm sure you know what the answer is, but the fringe planes are along the bisector. So fringe planes are going to look like that, all right? They're going to be, you have 180 degrees, so they're going to be at 90 degrees. But since the hologram is tilted, the fringe planes are also tilted in that material, okay? Again, you're going to have this refraction going in. And then I ask you to assume that you have no lateral shear, so there's no change, say, in the X or Y direction, but you do have about a 2% change in the thickness of this grating in the Z direction, okay? So in this case, if we didn't get any shrinkage in the actual material here, you're going to have some shrinkage, okay? And I just want you to see what the effect of that is. And assume that you're going to come in at the same angle here and calculate which wavelength gives you the best or Bragg matches the Bragg condition, okay? So essentially you're going to have something like, you're going to have a original K vector for the construction. It's going to look something like that, all right? And then after processing, you're going to have like a 2-degree rotation here. And here you have a K prime. And now if you illuminate this with the same angle coming in, let's see, is that what I'm at? Yeah, what reconstruction wavelength? So here, what reconstruction wavelength is going to give you a maximum now? All right. So this is going to have to change somehow to give you that matching condition. All right. Okay. So again, if you have any objects that you wanted to immortalize in a hologram, bring them on Monday or Tuesday. We'll have some extra material prepared, so if you want to take your hologram home, you could do that too. Okay, any questions on the lab? All right. Okay, good. All right, so the next thing I wanted to go over briefly is the a little side project here. I want you to do find a journal article, and I'd like the journal article to be in the last 3 or 4 years, okay, fairly recent journal paper. And I'd like you to do kind of a critical review of that paper, all right? And so by critical review, What I mean is that you find, really point out what the main point of that paper is. All right. So what is the main underlying theory that's involved? What is the main point of this paper? Again, not just restating what was in the paper, but really focusing on the highlights of that paper in your own words. Okay. And if there's some analysis in the paper that you want to use, or that's very important, point out the main aspects of that as well. So there's two parts for the in-class students. There's two parts for the online students. You'll only be required to do a write-up. But for the in-class students, basically there'll be 10-minute slots. And so we have, I don't know, I guess we're going to take up almost 2 class periods with our class. But there'll be 10-minute slots. You'll give like an 8-minute presentation. And I like in that time for you to present, again, the essential parts of that paper. What's the main idea? Why does it work? What's the significance of the paper? What's the significance of the result that's in it? What might it lead to in terms of new applications and so forth? There have been a couple of interesting presentations at the seminar series, actually. There was a Professor Ozkan from UCLA who was here a few weeks back, a month or so ago, and then Ian McLeod was presenting on similar topics with some digital holography methods. We haven't talked about digital holography yet, but we will, and there will be a demo lab for digital holography towards the end of the class course. Okay, so you'll give an 8-minute talk. Maybe have eight or 9 slides at the most. For your presentation. Maybe do a dry run, see if you can do it in 8 minutes. Because time is going to be kind of critical. I'm going to have to cut you off after 8 minutes in doing it. And then I'd like a minute or two for some questions afterwards as well. So it'd be sort of like a regular conference presentation format. So, and then, I'd like, maybe a 3 or 4 page write-up, which again summarizes the main aspects of the presentation. The write-up needs to be word processed. And again, I want it to be your interpretation of what the main results are, not just kind of a rewrite of the paper. So in doing this research too, you may want to look up a prior paper. If you have some interesting subject, result, but you may not understand what it is, you may need to go and look up maybe one of the other references that's given and read that paper as well. So it's not just maybe one paper, but understanding a main idea for a paper and presenting that and giving kind of a critical review. Again, very similar to what you do or should be doing in your research on kind of a regular basis, seeing if the paper is worth reading, are the results any good, how significant they are, understanding the underlying principles for the paper, all those are very important in doing your research. Okay, and then again, looking at this, it'll be due in about a month because we'll have the presentations on the 1st and 3rd of December. I think the last class day is December 9th, and I want to use the last class period, which is December 8th for us, to review last year's final exam, for review for the final. And I believe the final exam's on the 15th during this class period. I think it's 3:30 to 5:30 or something like that. So anyway, so that's kind of where we're at there. And then some possible topics, holographic displays, materials, different kinds of applications here for Bragg gratings, like in fiber, semiconductors, resonant gratings, photonic band gap structures, holographic filters. I would prefer if you didn't review any of my papers. Okay, I do a lot of papers on filters and stuff. It's kind of boring for me to see my own papers. I mean, it's a little ego boost, but it's okay. You can read my papers, but I prefer if you chose another topic. And if you're working for another group that's doing some research on holography, I would encourage you to do a paper outside of your area. Like if you work, say, for Nasser Pengambarian or Pierre Blanche or something like that, talk about something, broaden your horizons, look at some other things that are going on. Okay. And then, there's lots of journals, optics. For some reason, Optics Express is not in there. It should be. There's a lot of good journals out there. And so what I would do is maybe in the next week or so, choose a topic. If you're having trouble choosing a topic, come and talk to me after class and I could help you find a topic. There's lots of interesting things going on. And kind of get started on that so you won't have a crunch near the end. Okay, and then the paper, you can turn that in on the last day of class, which is the week after. So you don't have to worry about your presentation for the first, if you're going to do it. And I'll come up with a list, kind of a schedule of who's giving papers when. I'll make a schedule, and you'll be either on the 1st or the 3rd, and I'll pass that out maybe a week prior, so you have a heads up on when you're going to be presenting. Any questions? Okay. All right. Okay, so moving on here. So again, let's look at this coherence problem. So if we have a laser, basically we have some emission profile for the laser. This is the frequency, say kind of the peak frequency of that emission profile. And if we had a single mode laser, and again, a laser was going to be formed by a couple of mirrors, M1 and M2, and we have some gain medium here, looks like that. And we get an oscillation here. And a single mode means in this case, a single longitudinal mode. And so we're going to have something that looks like a delta function. And so here we may have our mode spacings out here at C over 2L, where L is the cavity spacing, like so. But these mode spacings are such that they don't overlap. Only one of them, say, overlaps within that gain medium. And so here we may have a delta nu, maybe say on the order of 10 to the 5th hertz if you have pretty stable mode. And if we had for a Gaussian, if this mode looked like a Gaussian, we would have a coherence length that would be something like 0.664 times C over delta nu, and that would be about 2 kilometers in that case. So basically we have, we wouldn't have to worry about coherence length because, we have a nice, very long coherence length, so we don't have to worry so much about getting our path lengths very equal. But so let's now change this problem, and so now these modes are going to fall within the gain profile. And let's just look at the case where we have two modes oscillating, all right? All right, and so both of these, again, they're going to have some width to it, but we can model it kind of like a delta function. And so here we're going to have, say, nu sub n and nu sub n plus 1. They're going to be separated by c over 2 n L. If we have, all that was filled with some index, refractive index, and we'd have to account for that path length, additional path length due to the refractive index. Okay. So again, we have that our delta nu is equal to nu sub, say, n plus 1 minus nu sub n, and that's c over 2 L, for where L is the cavity length of that laser. So if we look at that, the power spectral density function that we have, so if we think of a power frequency function, spectral frequency function, that's going to be given by, say, the intensity of one of those modes times a delta function plus I sub n plus 1, delta of nu minus nu sub n plus 1. Okay, where, again, so these are just the I sub n plus 1, the intensities of those two different modes that we have. All right, so the question is now, so what is the coherence length for this system? Okay, so we can say, from our previous analysis that in terms of the power spectral density function, this gamma 1, 2 of tau, we can write that as the integral from minus infinity to infinity of phi of nu, e, or exponential of j 2 pi nu tau d nu divided by the normalized. Okay, so we have phi of nu minus infinity to infinity d nu. All right. So that's convenient, because now if we do that integral, all right, we end up with the following. So we have gamma 1, 2 of tau is now equal to, and we're going to factor out the total intensity. So we have that for our total intensity, which actually works out to be that function there, times I sub n times exponential of j 2 pi nu sub n tau, the first frequency, plus I sub n plus 1 exponential of j 2 pi nu sub n plus 1 tau. So just by subbing that into that, we end up with that. All right? Okay. So let's do a couple things here. Let's establish a couple constants. So we'll say we have a sub n is going to be equal to I sub n over I sub n plus I sub n plus 1, and a sub n plus 1 is I sub n plus 1 over normalized I sub n plus I sub n plus 1. All right. Okay, so, and then we also have that this is the case too. So these two frequencies are related to one another by a difference equal to the frequency corresponding to the mode spacing. All right. So we can write this now, this gamma 1, 2 of tau, as a factor. So we can factor out, since these two are related, we can actually factor out this term, right? And so we have exponential, because it's contained in both of these exponentials. So we have exponential of j 2 pi nu sub n tau times a sub n, right, we factored it out of there, plus a sub n plus 1 exponential of j 2 pi times c over 2L, which was the separation in frequency between those two, times tau. Okay, so we haven't really done anything except use the mode spacing relation in our equation and kind of establish these fractional values for the intensity. All right. Okay, so now let's play around with this a little bit. And so let's do the following. It may not make any sense right now, but we'll see that it helps look at this in a different perspective, which is important. So we're going to square it and then take the square root. Okay, it seems kind of stupid, but let's do it just for fun. All right. So if we square this, all right, so and then take the square root. So we'll end up with this gamma 1, 2 of tau. And we'll only look at the magnitude since we're doing these squarings and square root values, we'll get rid of this term out in front here when we do that. And so we have a sub n squared plus a sub n plus 1 squared plus 2 a n plus 1 times the cosine of pi c tau over L. And then we're going to take the square root of that. Okay. Well, if we have that an equals an plus 1 equals a half. So what that means is that we have equal amplitude modes in this relation. We can then use the half angle formula, which says that if we have, cosine squared of alpha equals 1/2 times 1 plus cosine 2 alpha, we can then rewrite this as being equal to, gamma 1, 2 of tau magnitude is going to be equal to 1/2 plus 1/2 cosine of pi c tau over L. Let's make that a square bracket. And that to the 1/2. And so this half angle formula is useful because now this is just cosine alpha squared, which is equal to the cosine of pi c tau over 2L. We have to make this half, right? This angle is half of that angle. And we don't have the square root anymore. So rather interestingly, we end up with a function for the coherence function, which is simply the absolute value of a cosine function. And the argument of that, within the argument of that is this path length associated with the laser cavity spacing. Right? So if we were to plot this, here's we have tau. So this is going to look like this. So it's going to start out at 1 when we have 0 for tau, right? And then it's going to drop to 0 when this is L over C. When tau is equal to L over C, that's pi over 2. So we get 0. And then it goes back up again, reaches the maximum at 2L over C. Then it goes back down again, and it keeps doing this, okay? So this is, really kind of interesting. I told this, I actually did this experiment, I think I mentioned this, and I told it to one of my other students, my grad students, and so he went and did it too, just for fun. And he found that, yeah, it does. He set up an interferometer. The way you can do this is set up a like a Twyman Green interferometer and keep increasing your arm length for that interferometer and look at the fringes. And so what you'll see is the fringes wash out, and then the fringes increase again, and then they wash out again and increase again. Now, this doesn't go on for infinity. There's a very broad function, decay function, that is kind of overlaid on here, which corresponds to the fact that if this was a perfect delta function, it wouldn't decrease, okay? But because there's some width to this, this result, there's actually a kind of a product of these two relationships for the gamma 1, 2. All right? And notice, too, that L is what? L is the cavity spacing of the laser, okay? So the visibility is going to wash out when you have your path length separated by about the cavity length of the laser. So like prior to the last lab 2, again, one of my students forgot about this and set it up with too long of a path length separation, and I immediately said we have to change this because that laser, so the helium neon laser is about this long, right? And there's about 2 modes oscillating. So that's all the path length you have to work with, okay? And if you go to the full extent, it's down here. Actually, you want it, up here. So by convention, this is about 1 over square root of 2, or 0.707 down, all right? So you actually, that's sort of the extreme. You want to cut that down a bit so that it's, still have high visibility. So again, this is kind of a very useful relation that you have. And notice we went from 2 kilometers for that single mode laser down to, maybe 30 centimeters. All right, so that's quite a drop just by having those 2 modes oscillating with slightly different frequencies. Okay, so in this, we kind of assume that the 2 amplitudes were equal to, or were equal to a half, or the same value. If we had, say, different amplitudes for these 2 modes, so, what if, this kind of drifts over a little bit, so maybe we have one that's here and one that's down there oscillating. How might that change this coherence function or the visibility function? Well, in that case, let's say we have a sub n equal to a third and a sub n plus 1 equal to 2/3, then our gamma 1, 2 at tau magnitude is going to look like this, where it's now 5/9 to the 1/2. You could plug those values in to this, the more general relationship that we had up here and solve it. But this is now equal to 5/9 times 1 plus 4/5 cosine of pi c tau over L to the 1/2. You can't use that squaring and take it to square root trick in this case because we don't have the amplitudes equal. But we have something that looks like that. And so what happens in this case is that we don't actually drop to a complete 0 here, but this kind of goes up and then back down again and so forth, kind of similarly. But the range in contrast that you end up with is not as great. Okay. If we were plotting the visibility, I should say, in that case, for the fringes, that's what you would see instead of something dropping to 0. Okay. Now, what if you may have noticed that we have that argon laser in the lab, all right? And so for an argon laser, here you have a much longer cavity spacing between the mirrors. The mirrors are near the ends of that. They're not quite at the end, but they're pretty close to the end in that argon laser. And in that case, the there'll be maybe about 10 modes oscillating, all right? So how can we extend this if we have more than, say, 2 modes? All right, well, we can still have a function, power spectral function, phi of nu now, which is equal to, say, I sub n delta of nu minus nu sub n plus I sub n plus 1 delta of nu minus nu sub n plus 1. And, we can add however many we need out to, say, I sub n plus 1 delta of nu minus nu n plus 1. All right, so we have, again, just another set of delta functions, essentially, for the power spectral density function. And in this case, I won't go through the whole process, it's in the notes, but in this case what happens is that we end up with a function for gamma 1, 2 of tau, which is equal to 1 over n sine of n pi c tau over 2l divided by the sine of pi c tau over 2l. Okay, so what we end up with is now this kind of sine ratio function. And what that looks like, and actually if we put in n equals 2, in that case we end up with we'll have our previous result, okay? And if we plot this here, all right, so here for our previous case we had that, for 2 modes, the gamma 1, 2 of tau kind of drops down to 0 at L over C, and then it starts to increase, reaching a maximum at 2L over C. If we had 3 modes, what would happen in that case is that this would drop a little bit quicker, as you might guess, and then it peaks up a little bit. There's a little bit of a bump here right around that prior null, and then this goes back up like that. So this would be 3 modes, and with 4 modes this drops down. You have a cycle like this. Since it's even, it has the same null at L over C, and then goes like that. So again, so what's happening is this visibility function that we have, or this complex degree of coherence function, keeps shrinking, as you might expect, with more and more modes that are oscillating in that system. Okay, so we had this nice argon laser in the lab, so here, and if we have, like 10 modes oscillating, that translates into a coherence length that's about 3 centimeters. Okay, and for a lot of the applications that we do in my lab, that's not sufficient. Sometimes we need to have some really different path lengths. If we put lots of motorized stages in there to make some complex holograms and so forth, we're going to need a lot more coherence length. All right. So the way to do this, remember, so the mode spacing that we have from these standard modes that you would have. So here, so if we were looking at the laser modes here, so here is from the laser cavity modes, spacing like that. And again, this is on the order of maybe a meter for that cavity length, mirror separation. that then is going to kind of compress these different modes. Here's, say, nu 0, and this is C over 2LC for, for those cavity modes that are oscillating in your system. But what you can do is to put another filter to kind of filter out these other modes, okay, out of the system. And you can do this with another cavity. So you make you put another cavity in here, and this one has a much smaller spacing between, because again, the delta nu is equal to C over 2L, all right? So if we have, say, LE much less than LC, the cavity length there, now the modes are going to be, I didn't quite center that, but we'll just take it at here. Now the modes are going to be something like this that can oscillate. So these modes are no longer, there's too much loss for these. The only place where you have transmittance is right here and right here. Right where these cavity modes, so you basically have like a little laser cavity but no gain medium in it. And that's called an etalon. So what you do when you buy a big expensive laser like that is you buy an expensive etalon that's usually temperature controlled for maybe $5,000 or $7,000, and stick it in that cavity. And with that, though, you tremendously improve the performance of that laser if you're trying to do holography or some type of interferometry. Okay, and we have a temperature stabilized etalon in our system. We could set the temperature, and actually I have to go through and redo that, kind of show my students, because you kind of forget after a while, and then all of a sudden you notice the power dropping. Because what happens is, too, if the temperature is not set right, then this spacing kind of changes slowly. And so this nice peak here starts to drift down further here. And so it may start out, giving you a lot of power coming out, and then after a period of time it starts dropping, and then it stabilizes, and then it stabilizes at some less than optimum power output from that laser. So again, an etalon is a very important, basically a Fabry-Perot cavity, and I'm sure you're familiar with that from some of your other classes, but you can use it to great advantage in improving performance of lasers for different applications like holography. Okay, so now we've kind of looked at this visibility issue. So let's see how it ties in with the performance of different holographic materials. Okay, so we have sort of a visibility, a measure of visibility, and so we can actually tie that into evaluating the performance of materials. And see how sensitive the material is to changes in the visibility of the illumination beams that you're using. All right? So here, let's go back and kind of evaluate this from our basic principles, holographic principles. So we have an object wave here. So we'll just have it as a function of x with a constant amplitude and a phase exponential of j 2 pi chi sub a x, where chi sub a is equal to the sine of alpha a over lambda, so kind of the spatial frequency for that propagation, the object propagation field. And then we have, for the reference beam, we have r of x equals r exponential of j 2 pi chi sub r of x. Again, chi sub r is sine of alpha r over lambda. And again, so we expose as usual, and we have an intensity. And so we have A plus R times A plus R star, and then the resulting transmittance function, T of x, is some average transmittance plus a transfer constant of the material times the exposure time times A star plus R star plus A star R plus A R star. Okay, just like we've done many times in the past. All right, so we're going to use this though to look at some other insightful ways of viewing this this situation in terms of visibility as well. All right, so when we then reconstruct, right, we're going to reconstruct with the wave which is, we'll call it R prime, and usually it's kind of close to R, it doesn't have to be, or close to R star. But in either case we have, say, W of x now is going to be equal to, and let's make this a, we'll put a factor of 2 in here because it'll come out better in the end. And we can get away with just throwing a factor of 2 in there because this beta is a constant anyway, kind of an, almost arbitrary constant. And so we can kind of factor out 2 out of that constant, for instance, and put it out in front just to make the relationship simpler in the end. And so here, again, this W is obtained by multiplying that transmittance function by R prime. And so we have a R prime times R star. So if we're looking at this term, for instance, with the A in it, those should be squiggles. And we have the original object field, A. All right? So again, so W, the reconstruction field, is linearly proportional to the object field as usual. And notice we have, these two terms here, all right? And so those two terms are, so we have A squared plus R squared. And if we multiply that by tau, right, what is that? That is equal to the average exposure for that hologram that we just made, all right? Okay, and recall as well that the visibility, V, is, again, Imax minus Imin over Imax plus Imin, and we have, this basically times R prime for the reconstructed field. And so this visibility is equal to 2AR over A squared plus R squared. All right? Now, before I go on too, we can rewrite this visibility in another form. We can say that if we can define a beam ratio, as you normally measure your object beam, measure your reference beam, and if you take the reference beam intensity relative to the object beam intensity, that's equal to the beam ratio. And we can write this now as 2 square root of R over 1 plus R. So I think in one of the homework problems I mentioned the beam ratio somewhere in there, and that's what I'm talking about right there. But it's directly related to what we've always discussed as far as the visibility. Okay. All right, so now if we combine this average exposure and the visibility, we can notice here the exposure is embedded in that, right? And so we can say that we have 2AR is equal to a squared plus r squared times the visibility, or multiplying by beta tau times 2ar equals beta tau times a squared plus r squared times v, and this is equal to beta, a constant associated with the film material characteristics, times the average exposure times the visibility. All right? Now, so looking back at our reconstructed field, W, this then is equal to 2 beta tau times r prime r star a, and if that's equal to this, then is the product of those two. So we have r prime beta epsilon 0 times the visibility e to the j 2 pi chi sub a x. All right. And the again, so the magnitude of W is just equal to r prime beta epsilon 0 v. All right, so that's the real, say, amplitude of our reconstructed field. So one of the things that we're most interested in a hologram reconstruction is the diffraction efficiency. And what is that in terms of what we've just done? Well, the diffraction efficiency is equal to the intensity of this reconstructed beam, that we're interested in. This one corresponds to the object field. So we have our eta is equal to W squared over the incident field, WR prime squared. Okay. And so now if we look at that and multiply this, and use our result that we have here, the square root of eta is just equal to beta times the exposure times the visibility. All right. So if we were looking to kind of assess the performance of a material, we can make plots of the efficiency, or this more, accurately, the square root of the diffraction efficiency, either as a function of the exposure with different visibilities or of the visibility with different exposures, and kind of get an assessment for how well that material is performing. So, for instance, this would indicate what you would get with ideal conditions, all right? And actual materials have plots that kind of saturate or change slightly when you increase one of those variables. So most of the time, it's better to plot this visibility or with different exposures in your curves, or I find that more easier to do. And again, you can kind of get an assessment of how ideal that material is performing, in the sense of giving you a range of linearity that you can use in making a high fidelity hologram. So one kind of interesting result too is to note that you can get away with quite a bit on this beam ratio and still have pretty good visibility for your system. So again, beam ratio is equal to the intensity of the reference beam over the object beam. And if we have values of ranging something like this, the visibility that you get, of course, that's equal to 1. This is equal to 0.996. And even at a beam ratio of 2, where the reference beam is twice that of the object beam, this works out to be about 0.943. So you still get over 90% visibility, even with a beam ratio of 2. Okay. So there's one more little point I want to make to finish off this discussion on on coherence. And that is, if we look at the intensity, so we've been using our intensity as being equal to O plus R, and then we would square that and expand it. But what we actually have we have complex fields, and these are actually vectors, right? So to be complete here, we have to look at that square, and then not only that, if we have some coherence going on, we have to look at this for some period of time. So we have to take a time average of that. And if we expand that, we end up with, again, our usual intensities, I sub O plus I sub R, but then we have plus the time average of O R star. And, well, I should have maybe done one step in between here. These are vectors, right? So in doing this square, what we're actually going to do is we take O plus R, that's one vector, we dot it, right, since it's a vector product, with O plus R complex, all right? So we actually dot those vectors between those two in getting our result. And so after doing that, we end up with OR plus O star R, time average of that, times the cosine of the angle between O and R, all right? So again, so this was the idea that, if we have to worry about the polarization during the recording, and we usually like to keep the polarization state perpendicular to the table, so we can get around that. But if we had, for instance, the polarization in the table, so here's our object wave here, here's E sub 0, and a reference beam for some arbitrary polarization, and theta sub R and theta sub O, this omega angle that we have here is the full angle here between those two. And so the actual intensity now is equal to I0 plus IR plus 2 times the real part of OR star times the cosine of that angle. And the visibility, V, that we have is equal to 2I0 IR, square root of that, times our complex degree of coherence function, gamma 1, 2 of tau, times cosine of omega over I0 plus IR. Or if we use this beam ratio relation, this visibility can be written as 2 times the beam ratio to the 1/2 times the gamma 1, 2 of tau value times cosine of gamma divided by the beam ratio plus 1. So if we have a very high beam ratio, so as R gets large, what happens then is that the visibility is proportional basically to 1 over the square root of the beam ratio. All right? So we can simplify that a little bit if we have, say, a 100-to-1 beam ratio or something on that order. So in one of the homework problems, I think I asked you to evaluate, what the visibility is for kind of a general situation where you have a complex degree of coherence of some particular value and a inner beam angle of so many degrees and so forth between the reference and object wave polarization. All right, so that's how you would solve that. Okay, so that concludes that section finally on coherence, and you should be able to do your homework problem set 4, yeah. And I like that on Tuesday. The next subject that we're going to cover is is coupled wave analysis. And this is going to be one of the main, I think, one of the main topics for the class. One of the, something I'd really like you to take away from the class is how to evaluate the diffraction efficiency of the hologram. We've talked a number of times about the Bragg condition, and the Bragg condition is an integral part of the coupled wave analysis, because that provides us with this, with the coupling mechanism. This idea that we might have, say, a diffracted wave and a incident wave with a grating involved. We're going to get, again, coupling between that incident reference or reconstruction wave and the grating planes in that system. And not only that, but if you recall, we talked earlier, during the first couple of lectures about the selectivity. This is one of, a very useful aspect of volume holograms. The selectivity is very useful. You can get very high diffraction efficiency, approaching 100%. And so these factors are very important in making different types of holographic optical elements, filters, lenses, and so forth. All of these factors are important. And that selectivity arises from the fact that the grating it's volumetric in a sense that there are many interactions of that field that are going to take place as that beam propagates through that grating. Unlike the thin grating where we only had, say, one set of scatterers, that represented more of what was occurring at the interface between, say, the entering medium and the grating medium. That gives us a boundary matching condition or phase matching condition, which gives us the directional information. But everything that happens inside that medium determines or affects the overall strength of that interaction between that incident beam and the diffracted beam. So we're going to spend a couple lectures talking about that next, and I think you'll find it, hopefully find it very interesting, because there's a lot of things you can do there. Not only, you can also control polarization properties of the grating. We've made a number of elements to do that in the past when you didn't have other materials to do it. And so there's a lot of different things you could do. Again, you can control spatial characteristics, spectral characteristics, polarization characteristics, and even birefringent characteristics in the medium by manipulating the volumetric characteristics of that hologram. Okay, so we'll see you on Tuesday. And again, so Monday and Tuesday we'll have the labs. If anybody can come on Monday morning out of the Monday afternoon group or Tuesday morning out of that Monday afternoon group, be very much appreciated. So, and bring your objects that you want to enshrine in a hologram. So, okay.